Okay, great. So bear with me. I actually haven't done any math for 5 years now, but I'm happy to be here because this is we had a great time working on the algorithm, and I'm happy to see people are using it for other applications in math. So I wanted to mostly focus on some of the more technical parts of those polynomial chains that we use to deal with those humongous prime numbers. But also, I think it's good for redundancy. I'll try to give a recap of some of the key points we heard from Craig, so it can be a little more clear how all the pieces come together. Remember, one of the things Craig did was to try to give the intuition, and he gave the algorithm in a way that we did in our paper, which is motivating, like actually computing v to the p minus 1, which is not possible. So we'll try to restate things now in the real version that are actually true, and not just a motivator, and which was great for us to identify the obstacles and deal with them one by one. Okay, so the setting here, we're going to work in this ring R, which is the ring of the integers in the nth cyclotomic field. Now that's a little bit different than x to the n minus 1, but it's very close. So we're just modding out by the cyclotomic polynomial instead of x to the n minus 1. So n is the degree of k. And everywhere, the elements of this ring, we'll just call them v. And we're going to be working with the ideal generated by v. And you can write it in coordinates using the coordinate embedding 1, x squared, etc. And you can write it in some form, or you can write it in Hermite normal form. So also use the complex conjugate of v. And the product of the element and its complex conjugate is the norm in the real subfield. Okay, so this is a little bit more algebraic formulation.
So just a generic
Sure.
question. When you talk about Hermite normal form, so that's something you can do if you have an integer or rational lattice. Now if you take this number field with a canonical embedding,
no, I don't think there's a Hermite normal form for the canonical. No, right. So this is what I'm talking about here is if you have an element with an embedding, with the coordinate embedding 1 x squared. Yeah, you actually have the coordinate embedding. Then you've got a presentation as a subfield of z to the n. So that's the only time Hermite normal form can come up.
Or you can express it with respect to any z basis of the ring of integers.
Sure.
Okay.
Right. So the Hermite normal form isn't so important for anything, really. Okay, so when I say for computational purposes that we have an ideal, a lot of times I mean that you have the actual generating polynomials of that ideal in front of you. So you can write down the integral basis. Okay, and if we're going to be dealing only with the inner products, then I'll just say Gram matrix explicitly. Okay. So the recap of one of the things that we covered in the morning, let's call it the short multiple lemma. And Craig also called it implicit lattice reduction. And so that means for vectors, or actually elements in this ring, if you're given the element times its complex conjugate and the ideal written in some coordinates, and so you could write it in the Hermite normal form if you wanted because it's in coordinates, then you can actually produce a multiple of v. W equals v times some multiple, where the multiple itself is what's short, not the element not the element w. Okay, so does it sound like we heard about this morning? Great, that's what we heard about this morning, where you can compute an element in this ideal where the multiple is the short thing. Okay, and that's where you could think geometrically that you're using the geometry given by v times its complex conjugate to get that. So A, this element, when it's expressed as a vector, is short-ish. It's shorter than the LLL bound. Okay, and its polynomial time in the same way that LLL is polynomial time. So that's one of the obstacles that we dealt with, and that's one of the ways you use V times V conjugate. Okay, so that's the short multiple lemma. We'll call it that. Okay. The next lemma is, let's call it the congruence lemma. So we take P a prime, which is 1 mod M, and let's say that V is not a zero divisor of R mod PR, which I didn't spend that much time making my slides fancy. What?
Is M the same as M?
M, well, I think we were saying that N was the order, and so if you have the mth cycle atomic field, the order is a little bit less than M, right? The units.
N was the degree of
Yeah, N was the degree, and M is the mth. Yeah.
So N is phi of M.
N is phi of M. Yep. Okay, so if you take this element and raise it to the p minus 1th power, you get 1 mod p in the ring. That's the Fermat's little theorem. Okay? So that's great because if you have an element in the ring with very small coefficients, say the coefficients themselves, that's the coefficient norm, is less, they're all less than half of p, and you happen to know the product, a times v to the p minus 1 modulo p, well, that actually reveals a, because v to the p minus 1 is congruent mod m. That's all congruent to a mod p, and all the coefficients are small, so you can find it in the ring R. Okay, so that's where the congruence trick comes in. Okay, does that make sense? Cool. Okay. Then the next, so I'm trying to recap these ingredients, and I'll spend more time on the polynomial chains, because that's the technical part that we didn't actually get into so much detail in the morning. So the next lemma for this thing is, let's call it the small primes Euclidean lemma. So taking a bunch of small primes, just because they're easy to compute with, and two very big primes, p and p prime, both congruent to 1 mod 2m, so that their GCD is 2m. Then, working in a small modulo one of those small primes, these quantities actually make sense to write down. Remember, those are the same quantities that were enormous and impossible to write down with the enormous p's. So we're taking two of the p's with GCD 2m, and you can compute with them modulo and any reasonably sized prime. And you can use the Euclidean algorithm in the exponent, as Craig said in the morning, to calculate v to the 2m mod that small prime. Okay? And then if you've got enough of those small primes such that the product is larger than the element v to the 2m, then you can actually get v to the 2m by using some Chinese remainder theorem variant. Okay?
So what's the point in using two p's at the end?
Well, you know, the two p's right here,
The big ones.
the two big ones, because you wanted to have the GCD of these two big humongous integers be 2m, so that when you are able to compute these values mod p, you can do some.
If you use only one, can't you choose a small? Oh, you want p to be big in order to.
The capital P's need to be very big, so you can get that congruence relationship on the other page. And then the reason we're just taking two p's is so because we want to get this exponent down to a reasonable size, so we can actually write the element down. We like to write the element down over the integers, but.
So the GCD is actually 2m. It's not that 2m divides.
The GCD of those things is 2m, right? So we didn't deal in the computability of finding that, but there's a lot of primes, and Primality testing is fairly efficient, so I'm sure you can find two big primes like that without too much trouble. Okay, so you got these two humongous primes, v to the exponent of p minus 1 and v to the p prime minus 1, modulo a small prime, so you can actually do your arithmetic feasibly, can give you v to the 2m. Okay, does that make sense to people? Because you can do the Euclidean algorithm in the exponent. Okay, so I'm not spending that much time on this, but this is just one of the things that Craig mentioned in the morning.
So what you would do is the Euclidean algorithm on p minus 1, p prime minus 1,
Right?
and you apply the operations on these powers of v
Right.
at the same time.
Exactly.
That's-
So you can divide. You can take these things and divide them against each other in the ring mod
Or
p.
from the GCD you can just get what are the multipliers to get to n.
Sure, you can also do that.
And then
Yep. Okay, so that's how you. So given all the stuff, which I haven't shown you how to get yet, modulo these small primes, and you could use one bigger prime, but it's just I think it's faster if you use a bunch of small primes. Because you only need these product of the primes being greater than this number, which is reasonably sized. Okay.
Suppose you're using one bigger parameter, you might not need to use a p prime.
Yeah, but you probably could get away without it. But.
You can just take over mod k.
Okay, but I don't think that helps you efficiency-wise too much, maybe by a factor of 2. So anyway, that's how you get v to the 2m mod of the small primes and v to the 2m computable exactly in R, that ring of integers.
The p prime is supposed to be also larger than p to the n over 2.
Yes, yeah, yeah. Yeah, because what this is about using the knowledge of these exponents. This lemma is about using the knowledge of v to the p minus 1 and p to the p prime minus 1 modulo those small primes to actually get v to the 2m. Now we're going to you have to use the polynomial change, which I'll get to show you how to get v to the p minus 1 and v to the p prime minus 1 modulo the small primes. Okay, so once you had those in hand, this explains how you get v to the 2m. Okay, so that's the next lemma in our theorem. Okay, and then the next lemma is you can, given v to the 2m, you can create a v. You can recover v, which, of course, there's 2m possibilities for it. Just multiply by 2mth root of unity, and you get another one. And so I want to get to the polynomial chains, but I'll come back to this if people want to see some more details of the discussion of this. Okay? So with those lemmas, let's just recap our strategy for getting v back again. Okay? So we're going to choose our two big prime numbers, bigger than that LLL bound, both 1 mod 2m, and with the GCD also equals to 2m. Okay? And we're also going to avoid certain prime numbers where v is a zero divisor in R mod PR. That's a technical condition. You can see why it's going to come up when I do the polynomial chains, because you have to do a division. Okay? But it's not a very onerous condition. It's easy to satisfy it. Okay?
If you don't know the v, how do you know how to choose the p properly?
Let's see. How do you do that?
You know, the ideal generated by v, so p should just be cofine to the index of that ideal.
Yeah, that'll work. Yeah. Or maybe you could also use the norm of v, which you can.
Which is the norm of that ideal.
You can compute the norm efficiently. Okay. Okay. So then what we're going to do is we're going to use p and then separately p prime. You do them in parallel if you want. We're going to create these special chains of polynomials, and we're going to create the chains of polynomials one after another using that short multiple lemma. Okay, so which relies on LLL, that flavor of LLL. Okay? And every single term in these chains of polynomials that we'll go over will have reasonably sized coefficients. And by reasonably sized, I mean you can write it down. And that means, more technically, everything is less than the norms are less than the LLL bound. Okay? Okay? Then I'm going to show you how you actually get the v to the p minus 1 modulo any small prime you want, if you put a couple conditions on it anyway. So you can, and a v to the p prime minus 1. And then use that, we're going to do this using that congruence lemma that we went over, okay, which is related to Fermat's little theorem. And then, as we said in the last slide, knowledge of these two things can give you v to the 2m. And then you're going to take the root of v to the 2m and get v.
So can you remind me what the short multiple lemma stands for?
Okay, the short multiple lemma is, let's just go, what did you call it, Craig?
Okay.
It's the implicit lattice reduction one. So if you have a vector v in R, and you have its actual, and you're given, so for any vector in this ring, given the norm in the index 2 subfield, and given the ideal of it in coordinates.
So what do you mean by h and f of v? You are not given v, are you?
I mean of the ideal. That's a typo.
Oh, okay.
Sorry about that. Okay. Okay. So the short multiple says if you're given the ideal of v and the value here, you can produce a multiple of v such that the factor is short.
Thank you.
Okay. Okay. So that's just whoops. That's just reminding us of the whole strategy, like the whole structure of the proof. How the proof is going to go is you're going to choose these two big primes, and you're going to then create these chains of polynomials using that LLL version, which the details of which I'll explain. Everything will have reasonable size that you can write down everything, and everything will, everywhere you need to divide out, you can actually divide out. And that will give you v to the p minus 1 modulo some other small primes. And then by using the Euclidean algorithm in the exponent, you can actually get v to the 2m. And then you can get v. So that's the structure of the proof. Does that make sense? It's sort of it's just a recap of what we heard for the structure.
So the other small prime should also be co-prime to your little v, right?
The other small primes,
Ti.
because of zero divisor reasons.
Yeah, right.
Yes, but yeah, that would become.
Okay.
I didn't. That's missing here, but it's a footnote later when you actually have to divide by. I mentioned it, so I will say, yeah, you have to do some divisions. It's true.
But that's only for the polynomial chains, not for the calculation, or they're also in the congruence lemma also you need to make divisions? The small PIs don't need to do, or do they?
Well, you just count. You make the polynomial chains from the big prime,
Right.
and then later you use the polynomial chains
Because it's
for
every
a different small prime. Okay? So that, any more questions on the general flow of how the theorem is going to go? The big piece that we haven't covered is how you actually write down those chains of polynomials and how you use them to calculate these quantities, modulo a little prime. So then comes the technical part, where we actually have to write down these polynomial chains. So our motivation and goal is to allow expressions that have v to the p minus 1 modulo some small primes. And so basically our motivation is to create some equations which are going to let us do square and multiply using the bit representation of p minus 1. Okay? So the basic, I might as well just write this down because p minus 1, we're going to have to use the bit representation of that. So that's going to be k naught plus 2 times k1 plus 4 times k2 up to 2 to the r times k to the r. Okay? So each term in one of these polynomial chains is going to be using one of these coefficients here. Okay? So there's basically one term for every bit. Okay? So the term is going to encode one of those bits and an unknown v sub I. So v sub I is a different element of the ring, a different polynomial. And you can think of it as a fudge factor. Okay? Now, we didn't mention before, but in addition to producing this chain of polynomials, you're going to need auxiliary information that goes with them. So we're going to create a polynomial, and it's going to have this new fudge factor, which is going to be this v1 in it. And it's also going to come with some additional information, and that is the norm of that v1 in the real field, v1 times v1 conjugate. So you're going to need that too. We're also going to need the ideal of v1. So we're going to be creating these sort of fudge factors that are different every time and some information about them. Okay? So let's see here. So I'm going to explain how you get these in a minute, but the form of them is going to look like this. I can probably just write those down because we're going to need that again. So the first polynomial is going to be, in our chain, is going to be w1, and that's v to the k sub r minus 1 plus 2, or you could say times v squared. Okay? Times a new v1 variable that we're introducing, conjugate. And we're going to need this v1 times the v1 conjugate. And we're going to need the ideal of v1. So this is a polynomial in the polynomial chain, and here's some extra information. So we're also going to make a w2, which is v to the k sub r minus 2. So that's a different. By the way, the biggest bit in this is always 1, right? Because you take any number and you write it in base 2. The first one is always 1. So the kr is always 1. So this term is going to encode the bit, which is the second to last term. This one is going to encode the bit, which is the next one, which is k sub r minus 2. And also, it's.
How are we encoding the leading bits?
What's that?
How are we encoding the leading bits?
Well, it's right there. It's k sub r minus 1.
Well, there's a case of R.
How are we encoding that one?
Yes.
K sub, this is always equal to 1.
Yes.
Okay.
But
You don't need
Well, you're going to be starting from thing. It's like when you compute things by squaring and multiplying. The thing you start with is already there. You start with something, you square it, then you multiply it, and square it and multiply it. Okay, so W2 is going to be V2, the other bit, times this V1 squared. That's our new fudge factor. And except we're going to introduce a new variable, V2. Okay? And then we're also going to need, when we make that, we're also going to need a V2 and V2 prime. I guess I should be consistent. I should just put bars over the top of these. And you're going to need the ideal of V2 as well. And we're going to keep going all the way down to the last one, which is the last polynomial in our chain, W sub r, which is V to that first bit right here, times V sub r minus 1, which is the last fudge factor, squared. And a final fudge factor V sub r. And that also comes with V sub r times V sub r conjugate and the ideal of V sub r. I'm not sure if you need the very last one.
And which of these are you actually computing?
We're going to be, none of this stuff, we start off with none of this stuff. So I'm going to explain how to compute these things in a minute. This is just the definition of the polynomial chain. I'm going to say, how do you get them in some detail?
So when you say polynomial chain, does it mean that this is a chain of polynomials or that the length is polynomial?
It's okay, it's just a list of polynomials.
Oh, okay.
Think of it that way. Okay, so we've got R polynomials. We're going to be creating these R helpful polynomials with their friendly norms of the fudge factor they have in there and their ideal in there. Okay.
And this intermediate V1, V2 can be arbitrary. You can build a chain with any
Well,
choice you
they are going to come out of the construction. We can't.
So when you build W1, V1 comes out of it. Then this V1 is using the definition of W2. But
Yeah.
when you
That's
build
right.
the W2, you're also going to come out with some V2.
Right. And I'm going to explain how to do that.
Yeah.
Yep. So this is basically what we're trying to create something like this. And first, I'm going to explain how you create it, and then I'm going to explain how it's useful. So the point is, we need these list of R polynomials, and we need these R norms, and we need these R ideals. Of course, we already have these ones. Oh no, we don't. We only have V0. Sorry, take it back. I didn't mean to do that. V equals V0. What? Yeah. Okay. V to the 0 equals 1. So I'll just cross that out. Doesn't matter. Okay?
But there should be an equality sign.
Equals.
So you're saying that you're going to leave an algorithm that produces W1, W2, all the way to WR, such that there exists V1, V2, VR satisfying those properties. That would be the statement.
No. What I'm going to
Maybe you should show us.
let me okay, let me do it. But
yeah.
but what I'm going to do is I'm going to give you an algorithm that produces a W1, and from that you can compute these two quantities. And then you're going to do some more stuff, compute a W2, and compute these two quantities. Do some more stuff, compute more, all the way to WR, and these two quantities.
You have to show a test first.
Okay?
So, yeah, I think we should.
Then those equations are going to be useful. Okay? So let's see. How do we make this first term right here? Okay. So what do we have? We're starting off this process with the ideal of f, the ideal of v, and v times its conjugate. Okay, so well, we can certainly take v to the k to the r minus 1 plus 2, which is this exponent right here, k to the r minus 1 and the 2, which of course is the integer 2 or 3. Okay, so we're going to either create the third power of this ideal or the second power of this ideal, depending on this bit, if it's 0 or 1. So that's just ideal multiplication. You can do ideal multiplication. And here's v times its complex conjugate to a certain power, which is either 2 or 3. So we can certainly square or cube in the ring. Okay, so we get those two quantities. And now we're going to use these things, because what we have is, well, we've got this ideal, which is principally generated by v to this power, and you've got the norm of that element. So we can use that short multiple lemma involving lattice reduction to give a multiple, let's call it W1. And so W1 is v to that power times a short multiple. So that's the application of the short multiple lemma, and that new, let's call it V1 fudge factor, is that short multiple. Okay? So that's how you compute W1. Okay? It's just doing the same thing on the square or the cube. And by running the LL algorithm, implicit LL algorithm, you're going to get this multiple, and that multiple is guaranteed to be shortish. Okay? Meaning it's less than the LLL bound. Okay? And if it turns out that that is a zero divisor in R sub p, try again. Okay, because LLL will you could just run it again or look at the second shortest vector, and it's probably not going to be a zero divisor, but if it is, get another shortest vector. Okay, so that's a little detail. Okay, any major complaints about that? Okay, so just hopefully it won't be a zero divisor. But if it is, it probably won't be. If it is, just try again. Okay? Now, if you were to compute W1 times its conjugate, well, there'd be a lot of terms that you could cross out. In particular, you could cross everything out, all these V times V conjugate, because we had that to start with. So cross those all out, and you're left with W1 times its conjugate. I mean, sorry, you cross out the terms, and you're left with V1 times its conjugate. And so that's how you get this norm information about that newly computed fudge factor. Okay, the next thing we need to do is get the ideal of that fudge factor, V1. Well, that's this. You have the, if you look at this equation right here, you have the ideal of V. So you just divide out the ideal of V 2 or 3 times using an efficient ideal division algorithm, which probably you remember better than I do. Okay, so you've got the ideal here, and you can divide out by the ideal of V to some power, and you're left with the ideal of V sub 1, or its conjugate. Okay, so those are the that's the way you're using the LLL and the the version of it which gives you a short multiple, and that short multiple is the V1, and additionally you're going to get the norm of it and its ideal. And that's useful for creating the next term. Okay? Is there any questions about the first term here?
So what does shortest mean?
Shortest means its norm is less than 2 to the n over 2 times whatever the LLL bound is exactly. Okay? Okay. Now let's look at the next term. This is basically the same computation, but I'll just say you can do it by induction. If you want to go over it, I mean, you look at the ith term, you
Just do the same thing.
you do the same thing, except the main difference is that you now are encoding, you're taking this exponent which has the square, and so you square and multiply. So this is the squaring here, and there's the multiplication by the next bit over. Okay? And so you can also do the same thing with the norm in the index 2 subfield, the real subfield over there. And the short multiple lemma is going to be giving you your next W and your next fudge factor. Do the exact same thing to get the norm of that fudge factor and the ideal. And you just keep going all the way until you had an equation which involves the very last constant term of p minus 1, which everybody rightly observes is 0 because p minus 1 is even. But you still need to write that down. Okay. So we've got these things which are motivated by squaring and multiplying. So these equations have every single bit of p minus 1 in them. Okay? Does that make sense? Okay. Now we're going to use that chain to compute something we want. So what we want to do basically is create v to the big P minus 1 times the last fudge factor. So the last fudge factor here is going to play a special role because it's the one we would like to unfudge. We'd like to compute it exactly. Remember this morning we said we're going to compute something exactly and cancel it out? Well, that's the thing. So we would like to compute v to the P minus 1 times some fudge factor mod P. And by the way, you can do the same thing for another prime. So the way we do that is we work through this chain backwards. We set x1, or actually forwards. You set x1 just to be this first term right here, which is v to a power, which has the most significant bit and second significant bit times v1. So that exponent has the 2 most significant bits of p minus 1. Then you iteratively do it for the next term. So x2 is you're going to take x1, square it, and times it by the next one. Okay, so square and multiply. And if you write those terms out, you're going to get an expression which would has some extra terms that you don't want there. And those extra terms are v1 times its conjugate squared. So if you do this algebra, write in x1 squared, I wrote this hastily, so it's not pretty in tech. But you write this equation out, squared times W2, which is written down over here. And then you can divide out all the V1 terms. And you're left with this expression, which is V to the 4 plus 2 times this bit times this bit times this other fudge factor, which is still there. So what you've done is you've come to V to the power, which has the 3 most significant bits of p minus 1 and a fudge factor. So you can see how this is going. You continue the process, each time getting another bit into the exponent of V. Okay? And all these computations are modulo this big prime, capital P. Okay? So at the end, your rth value of x sub r, is V to the p minus 1 times your last fudge factor, conjugate, mod P. That's the thing we wanted. So you can see how these polynomial chains are really useful. We did all these computations mod P, and we never had to calculate V to the capital P minus 1 over the ring, because that would be explosive. Okay? Now, because V to the P minus 1 is 1 mod P, that's just this fudge factor, the last rth fudge factor mod P. Furthermore, as we said before, it's great that this is a smallish number, less than the LLL bound. So all the coefficients are actually really small, because capital P was so big. So you have this element over the ring itself, over R. Okay? So you get V to the R conjugate exactly. And the place where we had to be careful about dividing was exactly here. Here's where we want to make sure you can actually divide out. Okay? So as long as that's possible, because of the p's, and remember we said if you get a zero divisor, just take another one. It would be fine. And so that's the only detail. So otherwise, that's the algorithm for computing this last fudge factor exactly. So is there any questions about the computation of this last fudge factor exactly? Okay, that's great. So then we're going to reuse this for our small primes. So let Q be a different prime, where none of these VIs are zero divisors in R mod QR. Sorry about the notation. There's a lot of small primes, so just pick one. That's not bothersome in that way. And so this exact chain, that exact same evaluation can be done mod Q. So you use the exact same calculation to compute V to the capital P minus 1 times that fudge factor mod Q. Great, because we actually know that fudge factor exactly. So we know it mod Q, and you can divide out by it and get V to the P minus 1. So that was exactly the piece of information we needed for our theorem. And then you can take a bunch of these small primes. I guess I should have used Q sub I here, so that the product is big enough. Or you could take one large prime instead of that. But I like to use a bunch of little primes. But that's really a non-essential ingredient, that there's a whole bunch versus one. Either way, it would be computable. And then we use that small primes Euclidean lemma that we went over before, which does Euclidean element in the exponent with your other big prime, right? Because remember, we're going to repeat that. We did all this for the first big prime. If you do it all for the second big prime, you get V to the other prime minus 1 mod Q. And then you can use that Euclidean algorithm to get V to the 2m and then the 2mth root lemma, and that's how you give V. So that's the story of the polynomial chains.
So these PI, they play the role of your little Q.
Yeah, I should have put a Q sub I in there. Sorry about that. That's Q sub I. Yeah.
But you do the whole thing also for capital P prime minus 1.
Right, yes, that's right. Right. So I should have said right here, do the exact same thing for the capital P prime, so that you can do the Euclidean lemma.
Why don't you just arrange for there to be a single moderately sized prime q such that v to the p minus 1 is congruent to v to the 2m modulo q?
Yeah, we could have done that. I don't know. I mean, we could have done that.
And then you just compute it once mod q and note that it's small, and then you have it.
You mean instead of doing this Chinese remainder thing?
And using a p prime.
I haven't checked the P prime thing, but I'm sure it works. And this was just a way that worked, and that's probably that probably might work, and it's probably a little more clean. But I haven't thought about it. I don't know if you thought about it. Okay.
So is there an important reason why this m has to be related to? I guess this m is the m is cyclotomic. So is there a special reason why this has to be m?
Yes, because the order of, if you look at the cyclotomic field and you take any prime in that field, then the size of the multiplicative group is a multiple of m.
Because you need that congruence relationship.
Yes.
Oh, okay.
On the other hand, you could just raise to the power of p minus 1 over 2m and note that you're congruent to plus or minus an nth unit.
I hadn't thought about that. Maybe you could. Okay.
Modulo prime ideals, modulo probability prime ideals.
I mean, p is still prime. We're just not raising to the order.
P is not a prime in the cyclotomic field. It's
P is 1 mod m.
right?
So yeah, it's a prime. It's fine.
Sure, but you may not get the same anti-probability modulo the different prime. Modulo the different prime ideal values.
Right.
I mean, I think there's a fundamental reason you can't get. You have to get 2 to the v to the 2m, and you have to do another
What you need to do is you need to take
trick.
a prime and then
Go to a prime ideal, right, yes. Ideal that must be one.
Okay. So, anyways, those were the polynomial chains that avoided the huge exponent in the p, in the capital P.
So do these chains have any kind of geometric interpretation?
I didn't think of it that way. I just thought of it as building up the exponent.
No, I see the algebra, so I'm asking, is there any kind of, give these grand matrices, we know that these are ideals, you can think of them as lattices. Is there any kind of geometry, or is
You
just
should stay around for the rest of the week.
okay?
Yeah, I'm sure there is.
Do you know? Do you know?
Yeah,
that's
well,
okay.
yeah.
Okay. So, yeah, I mean, I'm just pretty much following the presentation in our paper from a long time ago and not really trying to optimize it further at this point.
That's what we want. That's what we want.
So v to the 2m, it defines v up to a 2m to the root of 1. If you think about an embedding into the complex numbers, you could just take one of those roots of it, and you would have it. So it's well defined for sure in that complex embedding. But now let's figure out how do you actually compute it. And the way we're going to do it is S is going to be a root of unity, a 2mth root of uni. And so you're going to, I think it's, 2mth root.
I mean, there's just polynomial factorization in a number field, yeah? X to the 2m minus something, equal to 0.
Is it? Yeah, maybe. Is that all it is?
Yeah, you x to the 2m minus v to the 2m. That splits completely into x minus v times x minus zeta v, etc. There's factorization. But this is how factorization works in the first place. So.
Okay, so we're just going through that. If you want to,
Well,
if we can.
usually people do it theoretically, but sometimes the same thing.
Okay, well, we did it in elementary terms.
So if you're going to implement it, maybe
It
it's
was already elementary.
Okay. Okay, so you got it. I got a computer program that does this already. So, I mean, we wanted to, compute it at a root of unity with some choices. So you have two m choices, and then it's embedding, it's a value at another root of unity. You might imagine there's two m choices there too, when you want to compute consistent choices.
I think really that your 2m should have been the LCM of 2 and m, because that is the number of roots of unity that you have. If m is even, there's no point in multiplying it by 2.
Well, in our case, I was just thinking of m as odd here.
In that case you do. The LCM of 2.
Right, I mean, because the cyclotomic, we were working on m odd for our application. So it's a little bit different if m is even. And so basically what we were doing was computing this ratio of v at one root of unity to v at a different root of unity. And you can compute that ratio efficiently by using a different prime number. You want me to skip this part?
No,
Okay. Okay.
But what is 2mc minus dv? Oh, that is.
So I'm just going to, I want to compute the ratio. I want to say if you know v at one root of unity, you can get v at the other roots of unity. Okay? So then you can put it together to get v exactly. And so I'm just going to take a large prime, which is minus b mod 2m. Okay? So this large prime is 2mc minus b, and then raising everything to the q using Fermat's theorem. And so you can actually take this 2v to the 2m, raise it to that cth power, and compute that it is v of x to that negative b times v to the b. Or you can think of that as the Galois conjugate here. And that's a number mod q, but since q is pretty large, you can get these over r. And so you get the ratio here. So if S is one of the mth roots of unity, this is what you're going to do. You're going to evaluate it. You're going to take v to the 2m at one of those root of unity, choose a 2mth, or choose an mth root of that in the complex numbers, and then use this formula to get v at a different root of unity by just taking this computed value here and dividing out by that root of unity to the bth power. And do the algebra, and that gives you v to a different root of unity. So you just try that for a bunch of primes, and you get v evaluated at all the roots of unity. And if you get v evaluated at all the roots of unity, then you've got v, period. Okay, so maybe there's another way of doing it, but this way works. Okay, so those are a little more details about this root thing. Okay? Yep. Well, I was trying to write the Galois conjugate here, and if you write v in coordinates, as a polynomial, if you take all the x's and raise those to the negative b, that's a way of getting the Galois conjugate. And that's, yeah. Yeah, so I didn't actually define x, sorry. So that's that lemma, and that's pretty much it.
But you were going to talk more about your papers that came later?
Yeah, no, it's it for that little section. I can keep talking about other stuff if people want. So this is some stuff I just thought of that I think is pretty interesting. Maybe you can think about this and maybe it's wrong. I don't know. But so, we were basically working in the cyclotomic ring instead of R. And sometimes we would, we were working x to the n minus 1, these cyclic polynomials, instead of the actual ring of integers in the cyclotomic field where n was a prime. So that clearly decomposes as the ring of integers plus another copy for the x minus 1 term. And of course, all these algebra stuff is really easy in the z component, so we pretty much can forget about it. And if you've got f times its complex conjugate in z, finding f is pretty easy. So we don't need to talk about that. Take the square root. But we didn't really talk too much about these coefficients a sub I in the coordinate embedding. And so when we have this ideal of V, it's presented as a bunch of polynomials which are some a sub I multiples of our V. Right? That's how you get your ideal. Let me just write that down. So we've got our V, and we've got, and that ideal V, you can think about it as a set of a sub I times V. It's just a list of polynomials that generate that ideal. Okay, so what if we shift our focus onto those instead of V? Because we started with this, and we started with times V conjugate. If we shift our focus onto there, it can be kind of interesting. If you write this in a matrix, it's going to be, unimodular. I meant unimodular instead of unitary. You can focus on the lattice instead. So our theorem says that given this ideal, which are these products of, so I've shifted from V to F, sorry, because I copied the slide over. So you're given this ideal of F and F times its conjugate. It says you can recover F, but you can also clearly recover all of these AIs. And everything is up to a unit, where U times U conjugate is 1, which is a mth root of unity. And so just notice, if we're just starting from this ideal and this norm, there's some easily computable pieces of information. First of all, from these elements a sub I sub F and F times its conjugate, so this is when I was doing this late at night, you get a sub I times its conjugate in R, right? Because you just take one of these terms, times it by its conjugate, and divide out the F's. So you can get these polynomials in R which don't involve F anymore at all. And if you look at the constant term of that polynomial, well, that's the dot product of these two vectors. Okay, so that's the same information that's in the Graham matrix A sub ij. Okay? So this easily derivable information is the Graham matrix of AI. So let's just say you've got Graham of A sub I. Easily. Now the other thing you get is we've got some more interesting stuff here because these are actually polynomials. Since you've got all these A sub i's times F, well, we can figure out what X times A sub I is in terms of the other AIs. So just, how do you do that? Well, we want to map X to some bunch of integers times all of the AIs. And so how are we going to define these coefficients? Well, if you just take X times A sub I of F, which is a quantity you actually have, that's in the ideal of F. So you can figure out using these lists of polynomials, you can figure out what those coefficients Gij are. So you can compute this mapping from X, which goes from AI to a sum of G sub ij X to the, A sub j.
What is X? Is X your polynomial variable?
Yeah, it's polynomial variable.
And are you multiplying by X? Is that what you're doing?
Yeah. So, so I want to, from the information that were presented in the GS data, which is these polynomials for this ideal and V times its conjugate. Well, I just reminded you that also easily encodes this Graham matrix of those AIs. But it also encodes this information of what a mapping would be, an automorphism generated by X. So X mapping A1 to some other linear combination. That's pretty, I think that's kind of interesting because it's, you can do the same thing for X squared. So you can think of this as a group action. So you can think that the data in our theorem is the same data of a gram matrix and data for a group action. Okay? So I'm trying to give a warm-up for what's coming.
Yeah, right. Thank you very much.
Okay? So that's great. So these are two easily derivable quantities. And I think it's what's the difference between these two pieces of data? Well, if you just focus on the situation of these AI coefficients, let's try to see if we can use the gram matrix and this group law to get let's see. So let's try to learn something about A1 from these two pieces of information, the gram matrix and the group action.
Can you repeat what group action is again?
Okay, so I wanted to say you can multiply by x. So that if x was an element, so let's write a group is identity x x squared up to x to the n minus 1. Okay? Okay. So remember, when I shifted gears here, I'm back to the ring of z of x modulo 1 minus x to the n. Okay. So this group, so you've got this group here, which is a cyclic group here of order n, and I want to tell you what does x do to these vectors a sub 1 up to a sub n. Okay, and what it does is it works by sending ai to a linear combination of the other aj's. So that's what I mean by the data in the group action. Okay. So if you focus for a minute on one of these terms, like a1, can we actually get all the a1 times aj conjugate values? Well, let's think about that for a minute. Well, the x to the eth term of a1 times aj conjugate is the constant term of x to the minus e times a1 times aj bar. Okay? Okay, so I'm going to use the group law to multiply, let's see, how does this work? X to the minus e by a1. Because you know the coefficients for multiplying by x. You could figure out the coefficients for multiplying by x to the minus e and suppose those coefficients were h sub I. So the action of x to the minus e on a1 is some other linear combination of all the a's for easily computable integers h. And so x to the eth term of this polynomial is the constant term of this polynomial. And I do some algebra on that, and so that's the sum of all these integers times the constant terms of a1 times aj conjugate. Those are exactly the elements in the gram matrix. Okay, so if you have that gram matrix and you've got that group law written out in front of you, then you can actually get a1 times a1 conjugate and a1 times all the other conjugates too, which is like the ideal of a1. So it's the same setup as you have in the plain old Gentry-Szydlo algorithm. So that is meant to be not a proof or anything, but it's meant to be inspiration that says if you shifted gears to the AIs and just look at the gram matrix and a group action, you can turn those previously structureless vectors of AI into something which makes the AI look like elements in a ring. So that group action can turn these vectors into ring elements effectively. Okay? So that's an elementary just restatement of what you can do from this with some algebra. And I think that's, without knowing exactly what you're going to talk about, I think that's maybe a warm-up into talking about giving lattices from gram matrices and actions by groups, how you add structure onto them. Okay, so that's what I wanted to talk about for that part. Okay, so then that was, I was just mentioning, you know, you also lost information in the Graham matrix. So if you've got these AI vectors that span a lattice L, you've got a matrix A, and A times a unimodular is just a different basis. And the Graham matrix also loses other information because if you switch around the order of the coordinates, switch the first coordinate with the second coordinate, all those inner products come out to be the same. So you could notice the fact that if you do a sign permutation matrix in front of a basis, the Graham matrix of that is the exact same thing as the Graham matrix of the original thing. So really, if you're just given the Graham matrix and nothing else, you've lost a lot of information. Okay? So I'm just hand-waving, saying the group law sort of rigidifies the lattice and nails down some of that ambiguity. Okay, that's supposed to be inspirational, but not a proof. Okay? So that's the stuff about our algorithm and a little bit of, you know, segue into it. Now, if you want me to keep talking, I can talk for a couple of minutes more. Okay? Because a while back, I was interested in what if you could try to make this even harder? What if you realize, you know, we've thrown away all this information by only looking at the Graham matrix, because we effectively needed the Graham matrix plus the group action, because that's kind of equivalent to getting this ideal and the norm. You basically need those two things. What if you throw away all this information and only look at the Graham matrix? In other words, let's just think about a lattice problem where you're given a Graham matrix only, and you want to find a basis. So somebody hypothesizes that there's n vectors u1 up to un, and gives you the Graham matrix of them. But we promised you that there's an embedding into Zn, but we don't know what it is. But I'll give you the Graham matrix. Can you get back u1 up to un? Clearly, you cannot get it back uniquely because it's not defined. It's not well defined because you could switch the order of the coordinates and get the same answer. So here's a problem, which I was calling the orthogonal lattice problem. But you could also give it a different name if you want. You can call it the Graham matrix factorization problem, or shortest vector problem in a determinant 1. There's different names for it.
So,
Yep.
if you drop the integer requirement and
Yes.
just want an embedding in Rn, then it would be trivial.
That's trivial because just
Zalewski or some other, yes, we can factor easily.
right.
It's about getting integer back.
Everything's about integers, right? So given this Graham matrix, can you find another matrix with integer coefficients, which is a sign permutation times that original u? That's probably the most you could do, given this Graham matrix. Okay? In other words, given the geometry of these vectors, how they relate to one another, can you, and a promise that there is an embedding into Zn, compute it? Okay? I mean, if you can compute it, then you found u up to sign permutation. That's equivalent to finding all the short vectors in there, which all have length 1. Okay? So that's what I was calling the Graham matrix factorization problem. So you could just take that Graham matrix and do super powerful lattice reduction on it in exponential time, find the very shortest vectors on it. That's going to recover u up to the sign permutation matrix. And that's exponential time, so that's infeasible. But I think it's an interesting case, and I don't think it's been studied as much. Because we're finding the shortest vector in a lattice, which you've promised has an integral embedding, and it has a determinant 1 basis. Okay, so I don't think people have thought about that too much.
So in this for Zn, basically.
Yep.
So I don't understand this. If you have two solutions to your problem, is it necessary that they differ by a sign permutation?
I think so. I think so. I don't,
think so.
maybe it's not true.
Well, we can vote.
Okay.
Well, anyway, think about it.
Any rotation, any rotation that keeps the integrality constant would do.
Well, of the sublattice, but not of...
Of the sublat, you don't
yeah.
need the entire integer.
The sign permutation matrix will with respect to all Zn, but nobody says it has to be the
Yeah.
case. Just the sublattice should remain integral.
Yeah, I think so.
Well, so maybe you're right, but I'm framing the problem saying, here's your problem. Given U transpose times U, find a U prime, which is a sign permutation of it. It may not be that those are all the solutions, but.
Well, I think I can...
all of the orthonormal bases are the same up to permuting and changing signs.
So just take the vector 4,3 and its rotations, right? That is isometric, but should I take the square of it? Do it in Zi.
Look, I mean, there are
Oh,
only
no,
two n
right,
vectors
yeah,
of unit
4,
length.
3,
We've got to map to one another.
There are only two n vectors of unit length in Z to the n.
Yeah, but I don't take unit vectors, I take the determinant.
No, this determinant 1.
He was also requiring determinant
Oh,
1.
determinant
Determinant
one.
1
Okay,
and drop.
okay, okay.
So then I think that's true, that those are the only ones.
Right, but for the first one, that need not be true. The integer vectors Vi, you're not requiring.
Right, so I think it's a harder case, and I don't think that is the answer.
Okay.
Only for this problem here.
Yeah,
It's a very
lattices would
special
require
case.
subgroups.
So say if it's a determinant 1 gram matrix, and it has an embedding to Z, find it. And so you could find it with lattice reduction, because you've got that gram matrix, and you know if you kept reducing.
So this is again assuming the determinant 1?
Yes.
Okay.
So assuming, so say U is unimodular, U times U transpose is given to you, find U. So that's a problem that if anybody thinks is interesting, they can study it.
So, am I remember wrong? Don't
Huh?
you have a result in your paper showing that if you can solve the isomorphism problem?
Yes, that's what I'm talking about here.
Then you can find.
Yes. Yeah,
Then you can
So
find,
he's gonna tell us that.
Okay.
I'll tell you that.
then
So-
you can find what?
He'll tell us.
So he can solve this problem
Go ahead.
if you can solve isomorphism
Yeah.
of gram matrices.
That's good.
Yeah, so the beginning part was just saying, you
I
know.
thought that was the end of the story. That's fine.
No. This is just a problem, right? I'm just stating a problem. Also, that problem actually comes up because you can do another version of averaging on some quantities, you know, related to older variants of GGH and the n-true sign, which use that ring. So you say you have a public basis, which is, you know, so there's a private basis A and a public basis which is a hidden multiple of it, and you got a bunch of, let's call it a transcript. And I say transcript because there are some signature schemes where if you got a message in a signature, you can do some math and get a bunch of values that have this form. So say you have different linear combinations of the columns of A, which are different combinations of those basis vectors. And if these B's are uniformly distributed, you could compute this quantity, which is these signatures as column vectors. So you've got a column and a row. So you multiply them out and get an n by n matrix and do the math. And that comes out to be some scalar constant time of A times A transpose. And that's interesting because you could define, using that, this matrix G, which is the transpose of that public basis times that quantity you got from averaging, which is a matrix, times M itself, and do the math. And what you've got here is some quantity which is related to this unimodular matrix. You've got U transpose times U. So there is some practical motivation for this problem. It's not just one I made up. You could think of some types of signature schemes that leak enough information to give you this gram matrix here. And if you could factor that into U, or some version of it which has even sign permutation times U, then you could go back and compute the private basis times a different sign permutation. So in other words, you're getting the sign permutation basis, which is just a reordering of the basis vectors. So there are situations where this hard problem of recovering U or sign permutation times it would break some scheme. That's why it was interesting. Anyway, so there's the problem, and that's why it's interesting. And so how could we try to factor this? Well, certainly if you use LLL and BKZ or some exponential algorithm, you could find the shortest vector in there. It would just take a long time. So we've reduced that other situation down to finding the very shortest vector. But that's probably not going to work because that's exponential time. So what I did in some papers, I said, if you had a tool, which I would call a lattice distinguisher, then you could create an oracle algorithm, and the oracle algorithm would actually recover U. As long as you can use this oracle, which is often as you like for practically free, tells you whether two Graham matrices are defining isometric lattices.
Just yes or no?
Yes, just yes or no. Okay?
Is this for arbitrary matrices or determinant one?
Determinant for arbitrary matrices. Arbitrary matrices. So that's that result. And the idea of it is, so the theorem is, suppose we have an oracle to decide if these lattices defined by these Graham matrices are isomorphic. Then there's an oracle algorithm that will produce U prime, which is related to U. Okay? Okay? So, here's an example. If you take a couple of lattices, if you write, instead of column notation, use the row convention for the vectors, because it was easier for me to type the rows. So here's a lattice which has 3 1s and 2s on the diagonal, and here's one which has 1, 2, 3, 4, 5, 6, 7, 8, 9, and 2s on the diagonals. So that's written in coordinate bases. Well, it's very easy to see that these two lattices are not isomorphic because this one has a vector of length, squared length 3, whereas this one does not. So in some cases, and you could determine that, sometimes you can compute that, sometimes you can't. So there's an example of non-isomorphic lattices and related to the ones I want to use. Okay. So what I want to do is try to find an embedding of these vectors into Zn. I'm going to define an auxiliary lattice. I know I'm going quick because I just wanted to give some flavor of this result. But so, for some embedding of Vi into Zn, well, the span of twice of every single one is isometric to the span of twice the identity. So in some coordinates, it just looks like all 2's on the diagonal. So if you instead take the span of V1 and twice every other vector, you're going to this manufactured matrix contains that 2L matrix with index 2. And we also know the shape of its and this is wrong. We know the shape of its Hermite normal form. No, that's right. Okay. Its Hermite normal form has got to look like something like one of these in the row convention, because there's all these 2's. Those are in the lattice, and so you can subtract all those 2's off of here. So it's just V1 is going to look like some number of 1's and some number of 0's. Okay. Sorry, I mean the auxiliary lattice is going to have that shape in some embedding. And so there's some number of 1's, and let lambda be the number of odd coordinates of V1. Okay? So I want to create a way to figure out the number of odd coordinates of V1. And the way I did that was I formed, you can form this auxiliary lattice for any of those vectors using the given Graham matrix. And that auxiliary lattice is isomorphic to one of those lambdas, like lambda 1 or lambda 2 or lambda n, depending on how many 1's it has in it. And let's say that auxiliary lattice, if you could use your oracle to tell which one it was isometric to. So you could use that oracle and just figure out how many ones were in it. Okay, so then you do that, and you just pretend like you're writing down the first vector. We'll say, okay, well, it's got 5 ones. Let me choose those coordinates to be the first 5. So you're making some choices here. Let's just write those first 5 down as those 5 ones as the first ones. So you're making some choices in the order of the coordinates by doing that, which is fine because we have sign permutation matrix worth of choices to make anyway, which is n factorial. Great, so now let's try to do it with the next vector. So let's say this, you can use our oracle to compute the number of ones in V2, mod 2. And you can try to write the next row down. But should you put those, say there's 7 ones, should you put those 7 ones over here, or should you overlap them? So you probably want to know how many of the coordinates of V1 and V2 are both 1. So then you could ask the same question, how many of V1 plus V2 are 1? And then you can use some linear algebra to figure out how many coordinates of V1 and V2 are both 1, and therefore start writing down V2. Okay, so did I have a picture of that? Shoot, I took off that one. Okay, yeah, because I knew I was going to have that much time, so I didn't put that in there. So basically, by using this linear algebra, you figure out what V2 should be, and you say, well, where should I write down the 1 coordinates of V2? Okay, based on the number of 1s in V1, the number of 1s in V2, and the number of places where it overlaps. Then you do the same thing with V3, and each time you may need to do a little bit of linear algebra. And by the time you're done with calling this oracle so many times, you've actually written down all these row vectors V1 in a consistent way mod 2. Okay? So then you can, I don't have time, but you can do more tricks to get them all done in a consistent way, mod 4, mod 8, etc. Okay? So it is possible to keep calling this oracle to figure out information